In this tutorial, we will be going over how to utilize FluoroMatch Modular, from file conversion to running our script and creating an output table. The workflow that works best with FluoroMatch is liquid chromatography tandem mass spectrometry data, specifically high-resolution data. FluoroMatch has been tested against data from Q-Exactive, QTOF, and triple quad instruments, and the triple quad is not recommended. FluoroMatch accepts major vendor formats, including SciEx, Agilent, Bruker, Waters, and Thermo. Experimental designs other than liquid chromatography tandem mass spectrometry can work with FluoroMatch, such as MALDI and direct infusion. When you download FluoroMatch from the Innovative Omics website, it will be in the form of a zipped folder, so you'll need to unzip the folder and save it in a separate place on your computer. Additionally, before we get started, you'll want to make sure you have MSConvert installed so you can convert your files. MSConvert can be downloaded from ProteoWizard, and there is a link for downloading in your FluoroMatch manual, which can be found in the download. So we'll open FluoroMatch, go to FluoroMatch Modular, and FluoroMatch Manual. You'll see here a link for MSConvert ProteoWizard. Control and click to access the link. And this is the page that will pop up. You want to double check that the project is ProteoWizard, the platform is Windows 64-bit installer, and you can add your email if you desire. Make sure you click that you have read and accepted the license agreements and hit download. FluoroMatch utilizes three major input data files: the MSMS libraries, which are included in the software, the MSMS data, which is converted to an open source format, and the peak list, which can be obtained from an open source feature processing software, such as MZMine. The first step is file conversion. So let's look at the input files you'll need. You'll need two types of input files. The first is the MSMS data, and the second will be your feature table. The MSMS data will come from your vendor and will need to be converted to an open source format using MSConvert. Now that you have that installed, let's open it up. FluoroMatch, background files, FluoroMatch Flow, MSConvert 64, and you want to scroll down until you find MSConvertGUI.exe. To access the files you would like to convert, you'll want to hit Browse and navigate to the folder with those files. Select the files that you wish to convert and hit Open. Find the drop-down box for the output format and select MS2. Note that parameters for conversion are highly dependent on the vendor. Check the written manual for conversion parameters for each vendor, and keep in mind that this tutorial covers parameters for Agilent's .d files. Also note that only files with MSMS data should be converted to .ms2. You do not need MSMS files for every single sample. In certain cases, a few representative samples or a pooled sample will suffice. Now that the sample files have been selected, and we have selected the output format as MS2, let's find the Filters drop-down box and select Peak Picking. We want to go to the second MS level and Add. Going back to the left-hand side of the face, we want to select the 32-bit encoding and deselect the zlib compression. Go back to the Filters drop-down box and select Threshold Peak Filter. The threshold type should be absolute intensity. Orientation should be most intense. The value should be whatever MSMS signal you consider to be noise, and this will depend on your vendor. For our experiment and instrumentation, we will choose 60. For Agilent, this parameter is optional. Click Add again. Next, under the Filters drop-down box, select Subset, and in the number of data points, input a 2 into the first box. Otherwise, the code may error, and click Add. Double check that your parameters are as laid out in this tutorial, and the output format is MS2. Then click Start. As the files are converting, it will give you progress updates. It will go from processing to finished or failed. If it fails, just rerun that sample and it usually will work. Once the files are converted, they will appear in the same directory the vendor format files are found, but the icons will look different and they will now end in .ms2, not .d. For the sake of time in this tutorial, I have already completed the conversion and I will show you. Here are the original .d files and here are the converted .ms2 files, and you'll see that their icons are different as well. FluoroMatch Modular requires files to adhere to its naming convention. So now that they're converted, let's rename them. We can rename our files using the renaming tool found in the download. FluoroMatch renaming tool, lipid match rename.exe. The first thing we want to do is give our project a name, and I will name this 3M Light Water. Select the negative mode, as FluoroMatch currently only supports negative mode. The output directory is where you want the files to go once they are renamed, and they can go in the same file as they are in originally, which is what I will do. And then we simply want to drag and drop the files that we want renamed. So these are MS2 files. We want to make sure that they are under the data dependent MS2 tab. Close the output directory and click Rename Files. This pop-up is telling you please see the following file for the list of renamed files, and you can see that it's in the .d files folder. So if we open this up, we now have this rename list. It's an Excel spreadsheet that tells you the original file name and then the renamed file name. So if you need to reference that, that is where you can find that information. And then the new names after utilizing the renaming tool are 3M Lightwater _1 _DDMS2 negative .ms2. And this follows the correct naming convention that FluoroMatch Modular utilizes. The second set of files you'll need will be your feature table. Your feature table can house any information you wish, but it must contain these three columns: a row identifier, which is a numeric identifier for each feature, the mass to charge of that feature, and the retention time. If your experimentation utilizes direct infusion or imaging data, you can view the video tutorial on lipid match that is linked below. While this video tutorial is used for lipids, the process is the same for FluoroMatch and can be very helpful. Keeping in mind that FluoroMatch currently only supports negative data, your feature table should reflect that. Once you have your feature table set up in this manner, you are ready to run FluoroMatch. Now that we have the input files that we need, they're in the correct formats and the correct naming conventions, we can use them in FluoroMatch Modular. But we need to make sure all these files are organized in a certain way. The simplest way to do this is to create a new folder. And this new folder should house the negative data-dependent files that are converted to MS2 with the correct naming convention, and a negative feature table. One important note here is that you can only have one feature table, but you can have as many data-dependent files as you wish. If you have multiple experiments that you want to run FluoroMatch for simultaneously, you'll need to create a parent folder. Within the parent folder, you'll want to have your separate experiments in individual folders. For example, here we have folders for two types of aqueous firefighting foam, AFFF for short. We have 3M's light water version and a mixture of AFFFs provided from an Air Force base. If you click to open the 3M light water folder, you'll see that it is organized in the same way the single experiment folder is organized, with your .ms2 files and feature table. And the provided from Air Force Base folder is the same with your feature table and your MS2 files that are in the correct naming convention. To run FluoroMatch Modular, you'll want to open your FluoroMatch folder, double-click on the FluoroMatch 2.4 folder, the FluoroMatch Modular folder, and the FluoroMatch.mc.r file. When FluoroMatch Modular opens, you'll want to Control A to select the entire code, then hit Control C to copy the code. We want to make sure we are using version 333 of R. You can find this version in the FluoroMatch folder, FluoroMatch Modular, Rgui.exe. And simply Control V to paste the code. Your progression in the program will take place through pop-up boxes, and it's important to know that sometimes these pop-up boxes appear behind the current window. If you're not seeing this pop-up box, simply minimize your current window and you'll find it. The first pop-up box for running the program will ask what folder contains the files to use. Now we will want to input the folder with the files desired. For the sake of this tutorial, I will do the single experiment folder. Next, it will ask you for the library. The libraries are contained in the FluoroMatch folder that you downloaded. FluoroMatch 2.4, FluoroMatch Modular, FluoroMatch Libraries. Okay. Now it will ask for a retention time window parameter. This will be the retention time window that you'll find the MS scans under your features for identification, and it's based on the widths of your peaks in chromatography. We will select default, simply input D for this. The default is set at plus or minus 0.15 minutes. Keep in mind that you can, however, set the window parameter to any time that you would like. Okay. Next, the parts per million window will pop up. This is for matching experimental with library fragmentation. For example, 10 ppm plus or minus 5 ppm is recommended for an Orbitrap mass spectrometer. We recommend 30 ppm plus or minus 15 ppm for most QTOF instruments. Here we will use 15 ppm plus or minus 7.5 ppm as we confirmed the QTOF was well calibrated and gave accuracies on known fragments within this range. For mass accuracy window for precursor ion searching, we will use the default of 0.01 Daltons plus or minus 0.005 Daltons. Now we have the MSMS isolation window you used, which generally can match your acquisition parameter, which is the quadruple isolation window for ion selection for fragmentation. It is not recommended to use anything above 1.2 Daltons as it will decrease the confidence of the identification outputs. You can input 1 or D for default here. Threshold intensity cutoff is for the threshold intensity of your fragment scans. 1000 is the default here, but we will be using 60 for our experimentation. Each vendor's instrument has different thresholds, and this number should reflect your experiment's instrument and the signal to noise. A threshold of 1000 is recommended for Orbitraps. While 60 is quite low, it worked for our Agilent instrument, and that is what we will use. Now we need a little more information on the feature tables that we have selected. So let's take a look at those. This is asking us which column in the feature table houses the row identifiers. The row IDs must be numbers only and unique for each row. If your feature software doesn't generate numeric numbers for the row ID, you can just insert a column at the beginning of the table and start with number 1 and label each row that way. In our table, it is column 1, so we will input 1. Now the mass to charge column is column 2, so we will input a 2. Now it's asking for the retention time column, which is column 3. The next pop-up that you will encounter asks, what row does your numeric data start? In this feature table, it is row 2, so I'll input a 2. It's important to know that any columns other than retention time, mass to charge, and row ID may have any character in any row, and you can have any number of columns allowing for formatted tables to be used. Once you input where your data starts, there can no longer be any other characters for the row ID, retention time, and mass to charge columns, only numbers. We are done with the feature table, so we can close that. Additionally, any file that FluoroMatch will be using needs to be closed, specifically those folders with the .ms2 files and the feature tables. A mass defect is based on a molecule's exact mass and the number of types of non-carbon atoms. An upper and lower mass defect is used for increasing confidence in annotations which fall under an expected mass defect when fluorines are present in the molecular formula. Our default parameters are based on mass defects found in the EPA's PFAS structural database, and we will use the default values for the upper limit and for the lower limit as well. Minimum adjusted R2 value for all ion fragmentation confirmation. This pop-up box is not very important. We can input D for default, and this one as well, minimum number of scans for confirming fragments for all ion fragmentation. Not important, we can just hit D for default. The next pop-up box will ask the parameter for the minimum number of scans required for the fragment to be confirmed. For example, do you need to see 3 scans across the peak for confirmation or only 1? This will depend on your instrumentation. In the case of an Orbitrap and for most QTOF acquisitions like used in our experimentation, 1 is sufficient. The pop-up box should disappear. Don't worry, this is normal. If you want to make sure the program is running, maximize the RStudio window and look at the box containing the code. If there is a red stop sign, it means that the code is in process. This stop sign will come and go as the code is running. Once the codes are finished, the red stop sign will disappear and not return. It's still here, so the codes are still running. Another way to know how far FluoroMatch has run is to open the folder that houses your input files. There will now be an output folder. The new files will populate here, but for the sake of time, we will look at a folder that is already complete. Once the software has completely run, you should see in the output folder a file named ddms. By clicking on this folder, you'll see negative and negative by class folders. This is the order in which it performs the identifications. If you open the negative mode folder, you can see which classes have been identified by opening additional files. Once all the folders have been completely populated, it will generate the final files. You will know the final file by the FIN in the naming. This may take some time, in some cases hours, after all additional and confirmed files are populated, and sometimes even hours after the neg ID'd CSV is generated. Another way to run FluoroMatch is to run it with parameters that are already set in a CSV file. For example, let's go again to our FluoroMatch Modular folder. Here you will see files that are labeled as parameters. If we open one of these files, we can see that all the parameters are already chosen. The only difference here is that instead of selecting which folders to run for FluoroMatch and selecting which folder contains the libraries we need to reference, down here, we have to add them manually. So for the directory of inputs on a Windows computer, all you need to do is find the folder for the inputs. Click Control C to copy, Control V to paste, and then we want to make sure that these backslashes are changed to forward slashes. So we find the backslashes, replace with forward slashes. And once all of the backward slashes have been replaced with forward slashes, we want to also make sure that there is a forward slash at the end of the name. And then for the directory of libraries, that is the library that is found in the FluoroMatch Modular folders. Control C, Control V, once again Control F, find and replace. And once again, we want to double check and make sure that there is a forward slash at the end of this name as well. Also, you will need to double check that the column number matches the row ID, master charge, and retention time. So row ID should be column 1, master charge column 2, retention time column 3, and the row that the numeric data starts in the feature table is 2, so that is correct. Once these parameters are set, we need to make sure to save the new CSV and close it. So we want to save as FluoroMatch parameters Agilent QTOF CSV input. And you can save it as anything you'd like. That is just what I'm choosing to save mine as. Once it is saved and closed, open the R script in the FluoroMatch Modular folder, FluoroMatch MC-R. Upon opening the R script, we want to make sure that we save this R script with a new name denoting the use of a CSV. This is the same code that we used earlier, but this time we want to scroll down until we see CSV input. Here it is, and you'll see that it says false beside it. We want to change that to true, and this is case sensitive. It should all be in capital letters. Then we'll want to scroll down even further to find where it shows the parameters directory and the parameters file. Parameters directory dir and parameters file. Once again, you'll want to change these using the Control C and Control V functions. For the parameters directory, parameters directory Control C and Control V, where that file can be found. And once again, we want to highlight and replace those backslashes with forward slashes. Once it's highlighted, hit Control F. Make sure we select in selection only so that we don't replace any of the other backslashes. Replace the backslashes with forward slashes. You can replace them one at a time or replace them all at one time. Then we want to find the name for the parameters file. Control C. Control V. Here we want to select the entire code, so we will use Control A, Control C to copy the code. And once again, we want to make sure we are using version 333 of R. You can find this version in the FluoroMatch folder, FluoroMatch Modular, Rgui.exe. Control V to paste the code and run as mentioned before. And we are done. As always, we want to say thank you to Innovative Omics for their training, access to experts, and cutting-edge resources. Should you need, feel free to visit their website at innovativeomics.com and use this page for contacting them. Thank you so much.